Okay, here we go with chapter 2, motion along a straight line. You can see our objectives here. We're going to identify that if all parts of an object move in the same direction at the same rate, we can treat it as a point-like particle. We can identify that the position of a particle is its location on a scaled axis. We're going to apply the relationship between a particle's displacement and its initial and final positions. Apply the relationship between a particle's average velocity, its displacement, and the time interval. And we're going to apply the relationship between a particle's average speed, the total distance it moves, and the time interval. And then, given a graph of a particle's position versus time, determine the average velocity between the two times. All right. Kinematics is the classification and comparison of motions. So we restrict motions in 3 ways. We consider motion along a straight line only. We're going to discuss only the motion itself, not what's causing it. And we're going to consider the moving object to be a particle. In other words, condensed down. We're going to take essentially what might be a book or something like that and condense it down into a point space. So a particle is either point-like, such as an electron, or it's going to be an object that moves such that each part travels in the same direction at the same rate. So no rotation, no stretching, just as it's, like I said, imagine a book or a car or something like that moving in a direction. So the position is measured relative to a reference point. So in other words, the origin or the 0 point of an axis, we're going to call this 0. We have to call some point 0, so we're just going to put it there on the number line. And a position is going to have a sign. So if we're going to move one direction, in this case generally to the right, it's going to be considered a positive direction where the numbers increase. The negative direction is going to be the other directions where the numbers generally decrease. So a change in position is going to be defined as displacement. So this little delta right here, this triangle, is going to be considered to be delta. So delta x. Whenever I say delta x, that's what I'm talking about. The delta x is going to be the change in x. It's going to be the final position minus the initial position. So delta x is going to be defined as the final, which sometimes is referred to as x2, minus the initial position, which is sometimes referred to as x1. So for example, you got a particle that moves from x is equal to 5 meters up to x is equal to 12 meters. Your displacement is going to be this, which is going to be x2 minus x1, which is going to be this. So 12 minus 5 is going to be 7. And that displacement is going to be in the positive direction. So when it moves from 5 meters to 1 meter, the displacement, or the change in x, change of position, is going to be minus 4 meters. It's going to move in the negative direction. If you take a look at the number line here, you can kind of get the idea as to why that's the case. So from x is equal to 5 to x is equal to 200, back to x is equal to 5, your displacement is going to be 0. The reason is that your displacement is your final position, which is 5 meters, minus your initial position, which is 5 meters. The fact that you went out to 200 and then came back, for whatever reason, does not matter. Your displacement is going to be the difference between the final and the initial. So the actual distance covered does not matter. So displacement is therefore going to be considered a vector quantity. What that means when you have a vector quantity is that that vector, if you've ever seen Despicable Me, you know the villain there was named Vector, and he always claimed that it was because he had direction and magnitude. Well, same thing here. Direction along a single axis given by the sign, positive or negative, and then magnitude, the length of the distance, meters, or in the English or imperial system, it's going to be feet. So if you ignore the sign, we're just getting the magnitude of the absolute value. So the magnitude of a displacement of minus 4 meters is just going to be 4 meters. We don't have any idea what direction that's applied, but we know that the magnitude of it is 4 meters. So here are 3 pairs of initials and final positions, respectively, along the x-axis. and which pairs give a negative displacement? So you can see the answers there. The pairs B and C will give you a negative displacement. So you've got -7 minus a -3. That gives you -4. Basically, you're taking this value and subtracting that value. If you were to take this value and subtract this value, you'd end up with a positive. It wouldn't give you a negative displacement. Here for C, it's going to be the same thing. You're taking this and subtracting that, and that gives you a -10 meters. Okay, average velocity is going to be the ratio of a displacement, or the change in x, delta x, to the time interval in which the displacement occurred, or delta t. So your average velocity is going to be the change in x over the change in t, x2 minus x1 over t2 minus t1. So the average velocity has units of distance over time. Generally, you're going to see meters per second. So on a graph of x versus t, the average velocity is going to be the slope of the line. And the average velocity is therefore going to be a vector quantity. Positive means you've got positive average velocity. Negative slope means you've got negative average velocity. I don't know if I can zoom in on that particular graph. Let's see. So you can see here, you've got x on this graph, you've got t over here. So the rise in this particular case is going to be your displacement. The run is going to be the difference in time. So if you start here and end here, this rise from -4 up to 2, so 2 minus a -4 is going to give you your displacement. And then the bottom here is going to be the run. It's the difference in time. You ended at 4 seconds, you started at 1 second, so the difference is going to be 3. So the average speed is going to be the ratio of the total time of the total distance covered to the time interval in which the distance was covered. Average speed is always positive because you're not running at a negative speed. That's not going to be considered possible. So a particle moves from x is equal to 3 meters to x is equal to -3 meters in 2 seconds. Your average velocity is going to be -3 meters per second. But the average speed is going to be 3 meters per second. Because if you're moving from this position to this position, this is going to be your final. You subtract the initial. So -3 minus 3 is going to give you a -6. You divide it by 2. That's going to give you a -3. But the average speed you've covered from 3 meters to -3 meters, that is a distance of 6 meters total. Doesn't matter the direction. So you've covered that 6 meters, and you're going to divide it by 2 seconds, so that gives you an average speed of 3 meters per second. So note the difference here between the average speed and the average velocity. All right, 2.2. So given a particle's position as a function of time, calculate the instantaneous velocity for any particular time. Given a graph of a particle's position versus time, determine the instantaneous velocity for any particular time. And then identify speed as a magnitude of instantaneous velocity. So, instantaneous velocity, or just velocity, is going to be at a single moment in time. It's obtained from average velocity by shrinking delta t. The slope of the position-time curve for a particle at an instant is going to be the derivative of the position. This is where your calculus starts to come in. So a vector quantity with units, it's going to be distance divided by time. So the sign of the velocity is going to represent its direction. So velocity is going to be the limit as delta t approaches 0 of your displacement divided by the change in time, or dx dt. So speed is going to be the magnitude of the instantaneous velocity. So for example, You've got a velocity of 5 meters per second and minus 5 meters per second. And they both have an associated speed of 5 meters per second. So, following equations give the position x sub t of a particle in 4 different situations. You can see them there. In which situation is the velocity v of a particle constant? In which is v in the negative x direction? And then you can see the answers listed below. So, for example, you have a graph which shows the position and the velocity of an elevator cab over time, the slope of x of t, and also the velocity v of t is 0 from 0 to 1 seconds and from 9 on. And that's going to be a little hard to see here until I blow it up. During the interval from B to C, the slope is constant and non-zero, so the cab moves with constant velocity. So if we take this and blow it up a little bit, you can see the constant velocity running from B to C, or from time 3 seconds to time is equal to 8 seconds. If you take a velocity, which is the change in x divided by the change in time, you can see here where it starts out. It's running fairly close to 0. Then as you get up to B, you see some acceleration. And if you go from B to C, you can see that this length right here is constant. It is a constant rate of increase. The velocity here is the same. It does not change. There is no acceleration. Then as you notice, as you go from C to D, that the velocity starts to decrease and then eventually goes to 0 here. It's not necessarily that the car comes to rest, but you are seeing the change here in the velocity from this particular graph. Acceleration. Here we're going to apply the relationship between a particle's average acceleration, its change in velocity, and the time interval for that change. And then given the particle's velocity as a function of time, we're going to calculate the instantaneous acceleration. And then given a graph of a particle's velocity versus time, determine the instantaneous acceleration for any particular time and the average acceleration between any 2 particular times. So, as we discussed before, a change in a particle's velocity is going to be its acceleration. And the average acceleration is going to be the change in the velocity, the final minus the initial, divided by the change in time. How quickly is your velocity changing? Instantaneous acceleration is basically going to be the limit as delta t approaches 0 of delta v over delta t, and the same thing is going to be written as a is equal to dv divided by dt, the derivative of the velocity with respect to time. If you combine these equations from before, where a is equal to the derivative of velocity with respect to time, if you take this part out, this d and this dt right here, take that away, you're left with v. V is defined as the change in position with respect to time. And what you're finding out is that the acceleration is going to be the second derivative of position with respect to time. Acceleration, like velocity, is also going to be a vector quantity. So the positive sign means that you're moving in the positive coordinate direction. Negative means you're moving in the opposite. And it's going to be units of distance over time squared. If the signs of the velocity and acceleration of a particle arc are the same, the speed of the particle increases. If the signs are opposite, then the speed decreases. So for example, if a car with velocity v is equal to minus 25 meters per second is braked to a stop in 5 seconds, then the acceleration is 5.0 meters per second squared. The acceleration is positive, but the speed is decreased. And what that basically means is that as the car is moving backwards, but eventually gets slower and slower, the reason is that the car is accelerating in this direction until eventually this comes to a stop. So accelerations can be expressed in units of g. That can be convenient. A g is basically 9.8 meters per second squared, or g unit. So here's a checkpoint. You can go through this and you can decide what the answers are. Cross-check them with what you see here. And again here, let's take a look at these particular graphs. This follows along what we had before. If you take the velocity and you draw it out like we had before, you can see that as it increases here, what you are seeing is a constant rate of acceleration between points A and B. You are seeing here it is a constant rate because this is a line. Again, the line is going to be the slope and the acceleration is going to be the slope of that particular line. Since that slope is constant, that's what it looks like. Here, from B to C, there is no acceleration, so that's why the acceleration graph lies along 0. As you go from C down to D, you notice that the car is slowing down, so it would follow that the car is decelerating. So as you go from C to D here, you're noticing that the acceleration is constant and then goes back up. So, section 2.4. For constant acceleration, apply the relationships between position, velocity, acceleration, and elapsed time. You're going to calculate a position's change in velocity by integrating its acceleration function with respect to time, and then calculate a particle's change in position by integrating its velocity function with respect to time. Basically, what you're going to be looking at here are antiderivatives. In many cases, acceleration is constant or pretty close to it, and that kind of helps as far as some of our models are concerned here, at least in elementary physics. So for these cases, we're going to use 5 special equations. Now, note that constant acceleration means a velocity with a constant slope and a position with a varying slope. So in other words, if you get in, you look at these particular graphs here, position with respect to time, slopes of the position graph are plotted on the velocity graph. So if you take a look at this, the slope for velocity versus time, if this were a constant velocity, this is what you would see. And with a constant velocity, you're not seeing any acceleration. So it is, this is going to be, whatever the slope happens to be, it's going to be constant, not necessarily 0. I shouldn't have said that, but it's going to be at a constant rate because this slope is not changing. It is a constant, and whatever that slope happens to be, this is going to be the graph of that. So the first basic equation. So when an acceleration is constant, the average and instantaneous accelerations are going to be equal. So if you take the definition here of acceleration and you say the average acceleration is going to be whatever your constant velocity is minus the initial velocity, we're assumed here we're going to be starting at 0, and whatever time we end up achieving this particular velocity, it's going to be t seconds away. So then the average, or A, is going to be v minus v naught divided by t. If you rearrange that, you get this particular equation. If you take the derivative of this dv with respect to time, you get back acceleration, or the definition that we had earlier. For the second basic equation, we're going to take equation 2.2, and we're going to rearrange it. The average velocity is equal to x minus x naught divided by t minus 0. Again, having x naught appear whenever time starts. And again, if you rearrange this particular equation, this is what you come up with. Another way to look at this is that the average is going to be the initial plus the final divided by 2, so that the average velocity is going to be 1/2 of the initial plus the final. So if you take this particular equation, V average is equal to V naught plus 1/2 AT, which I believe is achieved. Let's see if we run across that here. The average. So V average is equal to V naught plus 1/2 AT. If you take this and substitute it into here, then you end up with x minus x naught is equal to V naught t plus 1/2 AT squared. And sometimes it's easier to see some of those with integration. I think the book will have some sort of description on that if you're interested in that. The other equations here that are of interest, you can see they're written here. And as a matter of fact, all 5 of these kinematic equations, you've got their equation number here, you've got what the equations are right here, and the table is kind enough to tell you what quantities are missing out of each one of these. So if you only have certain bits of information, then you can figure out which one of these equations is going to be useful for you and find the information that you don't have. So, following equations give the position of a particle in 4 different situations. They're all written out here. To which of these situations do the equations of tables 2.1 apply? The answer here is going to be this and number 4. Basically, if you go back here, try to match up these equations with what's going on in here, you'll find that 1 and 4 do have a match. You don't really have anything with a cubic function in it, so that's why we throw out number 2. And you don't have anything with time in the denominator, so that's why we throw out number 3. Free fall acceleration. So if a particle is in free flight, whether it's upward or downward, and if we can neglect the effects of air on its motion or drag, then the particle has a constant downward acceleration with a magnitude g that we take to be 9.8 meters per second squared, which is what we had defined earlier. So we're going to apply the constant acceleration equations, basically those equations in table 2.1 to free fall motion. So free fall acceleration is the rate at which an object accelerates downward in the absence of air resistance. It's going to vary with your latitude, how far you are above or below the equator, and your elevation, how far up you are. It's going to be written as g, again, 1g, which is 9.8 meters per second. It's going to be independent of the properties of the mass. Doesn't matter what it's made up of, doesn't matter how dense it is, doesn't matter how it's shaped, so on and so forth. The equations of motion in table 2.1 apply to objects in free fall near the Earth's surface, in vertical flight along the y-axis, and where air resistance can be neglected. The free fall acceleration is going to be in the minus y direction, value of minus g in the constant acceleration equations. The free fall acceleration near Earth's surface is going to be a is equal to minus g, which is minus 9.8 meters per second squared. The magnitude of the acceleration is going to be given by this. Don't substitute a negative minus 9.8 meters per second squared for g. G is just defined as this. The direction of the acceleration will be defined later. So if you toss a ball straight up, what is the sign of the ball's displacement for the ascent from the release point to the highest point? So the sign is positive. In other words, the ball is moving upward. What is it for the descent from the highest point back down to the release point? Then the sign is going to be negative. The ball is going to drop. What is the ball acceleration at the highest point? The ball's acceleration is always minus 9.8 meters per second squared at all points. In other words, the acceleration is always going to be the same no matter at what point the ball is in its trajectory. At its highest point, obviously, the velocity is going to be equal to 0. But the acceleration is always going to be minus 9.8 meters per second squared. So the graphical interpretation. Determine a particle's change in velocity by graphical integration on the graph of acceleration versus time. In other words, if you integrate the area from t0 to t1, that area under there is going to be the velocity, or the change in velocity. Same thing happens here if you're looking at a graph of velocity versus time and you integrate from t0 to t1, that area under there is going to be the change in position. So, integrating acceleration, given a graph of an object's acceleration a versus time t, we can integrate to find the velocity. Fundamental theorem of calculus gives that the difference here in the velocities is going to be integrating the acceleration with respect to time from t0 to t1. And the definite integral on the right can be evaluated from this particular graph, basically the area between the acceleration curve and time axis from t0 to t1. That is your calculus definition. Velocity is going to run very much along the same lines. If you integrate velocity with respect to time from t0 to t1, that's going to give you the displacement. It's going to give you the difference between x1 and x0. So, for example, the graph shows the acceleration of a person's head and torso in a whiplash incident. To calculate the torso speed at t is equal to 0.110 seconds, assuming the initial speed of 0. Find the area under the pink curve. So the area from here up to, let's see, 0.110. Okay, so this would actually be 0.040. The area basically between the t-axis and the graph there is going to be 0. If you look at it from B, the area here under B, it's going to be half of 0.060, basically from here, that time to this time. And that is going to be multiplied by the acceleration, which in this case happens to be 50, which you can kind of see as it hits right here, that that's pretty much what your acceleration is going to be at that particular point. Area of C is going to be basically the time difference here times 50, which is what it's going to be from 100 to 110. It's going to be the same. And so your total area is going to be 2 meters per second. The summaries here. I'm going to describe the change in position, your average velocity, average speed, instantaneous velocity and acceleration. And the first derivative of velocity is going to be your acceleration. It's also the second derivative of position. These equations, which I would suggest you either write down or put in a very handy place. Free fall, where the acceleration is going to be minus g. And that is a short description of what you're going to be running to in Chapter 2. If you have any questions, please do let me know.